So before applying the theorem, let's make two observations. So let Ni be the number of visits to I by the Markov chain. So this is obviously sum over all non-negative integers n of indicator that xn is equal to I. Now this indicator is just 1 whenever xn equals I, and it's 0 when xn is not equal to I. So therefore, each time the Markov chain hits I, it adds a 1. And if it doesn't hit I, it adds a 0. So therefore, the sum counts the total number of visits to the state I. Now note that expectation of this Ni is of course a expectation of the sum, and the expectation of sum is always the sum of the expectation. So therefore, expectation of the sum is sum of this expectation. Now this sum is an infinite sum, but since all of these random variables inside are non-negative, this is still valid. I'm not justifying it completely, but it can be shown that this expectation of this infinite sum is actually sum of this infinite sum of these expectations, and that actually uses linearity of expectation plus monotone convergence theorem. But let's not get into that. Let's just assume that this is true. This is just a remark anyway. And then what is indicator of what is expectation of an indicator is just the probability. So therefore, this is just the probability, sum of the probability that xn equals I, starting from I. Of course, the expectation we are taking under starting from I. Okay. So this EI always, as we have already said, EI always denotes the expectation with respect to the probability Pi. So therefore, starting from I, expected number of visits to I is just the sum of these probabilities, which is essentially sum of these PIINs. Therefore, what we have actually shown is that I is recurrent if and only if the expected number of visits to I starting from I is infinite. Similarly, I is transient if and only if the expected number of visits to I starting from I is actually finite. And this makes sense in the sense that if a state is recurrent, then definitely it's going to come back to itself with probability 1. And therefore, it's going to come back over and over again. So the moment it comes back, it completes one excursion. And then by Markov property, it will come back again. And then it will come back again with probability 1 and so on. So therefore, you expect that, so you expect that the number of visits to I should become infinite. At least what this result is showing is that at the expectation level, this is true. So expected number of visits to I starting from I is indeed infinite when I is recurrent. On the other hand, if I is transient, then starting from I, you may not come back to I at all. There is a chance that this won't happen. In any case, even if you come back to I, you will only come back to I maybe finitely many times. And that is what is observed here at the expectation level. Okay. So starting from I, number of visits to I has expected value finite. So this is intuitively obvious, but I just wanted to make this observation. Also in the proof, we have already seen that starting from I, the Markov chain will never return to I. This probability is just 1 over this sum. And this 1 over this sum is nothing but now we know is the 1 over the expected value of Ni starting from I. So in other words, this probability of never returning to I is actually computed, explicitly computed through the proof. And note that this is also valid when I is recurrent, not just when I is transient. When I is transient, this expectation is finite, and therefore this is a positive quantity. But on the other hand, when I is recurrent, then this sum or this expectation is infinite. And then by using the convention 1 over infinity equals 0, this would be 0. This probability would be 0. And that is the case when I is recurrent, right? Because if I is recurrent, then this is finite with probability 1. This first return time is finite with probability 1, and therefore this probability is 0. Okay, so with these remarks, now we are in a position to apply our result, and our application would be on the simple random walk on Z. So you suppose Xn is a simple random walk on Z starting from 0. And our goal is to check whether the state 0 is transient or recurrent. Now, as I said already, this is the importance of our result. If you want to do it from scratch, from the definition, then you have to compute the F00n, which is the first time. What is the probability that the first time it returns to 0 after n steps? This is not very easy to compute. And you have to do an exact computation of that, because you have to check whether the sum of these probabilities is equal to 1 or not. This is possible. In this case, it's possible to do that, but it's harder. However, we will not take that approach. We are going to use our theorem, which is now handy. We have already proved the theorem. And in order to prove the theorem, all we have to do, we don't have to compute F00n. We have to just deal with P00n. Not only that, we have to check whether P00n, this series, is summable or not. So therefore, it's not at all important that we have to compute P00n explicitly. Well, in this case, it's possible to compute it explicitly, and it's much easier than F00n. However, all we have to do is we have to finally estimate this P00n for large n, okay, so that the summability can be checked. So that's the method we are going to use. Now note that since just quickly recall what is simple random walk. So it starts at 0, and then every time you're just taking a step +1 with probability half and a step -1 with probability half. Now, in order to return to 0 in n steps, n cannot be odd, because if you start at 0, after odd many steps, you're always going to be in an odd number, right? Because at the first step, you are going to be either at +1 or a -1, and so on. So therefore, if n is odd, P00n has to be 0. After odd number of steps, you cannot be back at 0. And also, this is another way to think of it is, if you want to be back at 0 after n steps, then up to the n steps, you need equal number of +1s and -1s. So that cannot happen if n is odd. Okay. So on the other hand, if n is even, say n is 2m, then you just need m many +1s and m many -1s. Now that can happen. You have to choose, and you can choose these +1s and -1. You are at liberty where these +1s could be. That can be chosen in 2m choose m ways. This computation we have actually done even in probability theory 1, but let's just repeat it. So the number of ways this can happen, coming back to 0 after m steps, is 2m choose m, because you just have to choose the places where the +1s would occur. Of course, total number of ways is each step can be either a +1 or a -1. So that would be 2 power 2m. So therefore, the probability of returning to 0 after 2m many steps is just 2m choose n divided by 2 power 2. So if you write it in terms of factorials, it's just 2m factorial divided by m factorial squared times 2 power 2m. So therefore, we have to estimate 2m factorial and m factorial for large n. That's what we have to do. Now this, fortunately, is available due to Stirling's approximation, which says that as n approaches to infinity, n factorial behaves like square root of 2 pi n times n over e whole power n. It's in the sense that the ratio of this and this is approaching 1 as n goes to infinity. Now, of course, this is extremely handy for us. So let's just use that. So using Stirling's approximation for n equal to 2m, we get that when m is large, then 2m factorial just looks like this quantity here, which can be simplified. Well, it's not much of a simplification, but we are writing it because of the later simplification. It's written like this. On the other hand, m factorial is just this guy. This is direct. This is precisely the Stirling approximation written directly. Now let's square it to get that m factorial square behaves like this. Okay, which can be written like this. Now we have to take the ratio of 2m factorial. We have to divide 2m factorial by m factorial square. So that would definitely, now there'll be a lot of cancellations. So if you do that, you'll see that this m power 2m will get cancelled, e power 2m will get cancelled, 2 power 2m will remain, and then also here, this 2 will get cancelled with this 2, and when you divide by this, you'll get a square root of pi m in the denominator. So all you will be left with once you divide 2m factorial by m factorial square is 2 power 2m in the numerator and square root of pi times m in the denominator. So this will be valid as m approaches infinity. By the way, all of these approximations, all of these are statements about m large. So as m approaches infinity. We didn't write it explicitly, but it's obvious. Okay, so we have almost estimated this probability. So let's do that now. So we've already shown that 2m factorial by m factorial square behaves like this as m approaches infinity. Now P0, 2m we know is this quantity divided by 2 power 2m. So therefore this 2 power 2m will get cancelled, and this will tell you that as m approaches infinity, P0, 2m is just behaving like 1 over square root of pi m. Which is great because we know that this series is summable. This series is not summable. This is constant times 1 over square root m. We know that it's not summable. So since this is not summable, this estimate is going to reveal that P0, m is not summable either. And that shows that 0 is a recurrent state for simple random walk on Z. Now, if you actually want to show the same fact from the definition, it will be a lot more work. So this shows that why this theorem is useful. We'll apply this theorem in other places, other examples as well, but this is the first example where this theorem, the use of the theorem is clear.